All right, welcome back, everybody. So it is time to dump deep into more of the data science. So I talked to Chad, a couple of you guys. You're definitely eager to get to the data science. The review they said was helpful, but let's get into the data science, and I fully agree. We need a joke to get started with to get everybody out of their email and back present from lunch. So here we go. This is my door closing joke. So first of all, how many people here are math majors? Any math majors in here? Perfect. Math major. What's your name? Pavan? Perfect. And any, let's see here, any electrical engineers? What's your name? Pontus. Pavan and Pontus? And I'm probably saying it completely wrong, but it serves me right for picking on you two. And any accountants in here? No, nobody working on Wall Street? What was your name? Clay. So Pavan, Pontus, and Clay, right? What was the name again? I was correct. Okay, good. All right. So a guy goes up to a mathematician. He says, Pavan, what's 1 plus 1? Pavan says, very interesting question. She goes up to the whiteboard and starts writing pages and pages and pages and pages and pages and pages. And finally she says, therefore, after we finish inventing the entire system of mathematics from elementary logic, you can see that we have proven 1 plus 1 equals 2. The guy's like, I did not understand any of that. Like, sure, maybe Bertrand Russell did this once and it took him 200 pages, but that was way over my head. I know who to go to. So he goes up to an electrical engineer, and it was Pontus. He gets it to Pontus and says, Pontus, 1 plus 1. Pontus pulls out her laptop. Type. Well, according to the Intel Pentium processor, it's 1.9999999999800000001. Guy's like, oh my God. Electrical engineers, I thought we moved past slide rules. What's up with this whole IEEE floating point arithmetic? I know who to ask. So he goes over to Clay, and he says, Clay, what's 1 plus 1? Clay gets an extremely serious look on his face, looks around. What would you like it to be? Welcome to Wall Street, Clay. All right. I use that one to close the door because I'm usually looking around at the door, but the door was already closed. All right. So welcome back. So this morning we talked about just the big ideas of data frames and the vocabulary of machine learning. And we briefly looked at Lab 1 k-means, data types, MLib data types. We're not going to spend any time on this lab whatsoever. We're going to jump straight into the model. But just remember we talked about dense and sparse vectors. Real simple. Sparse vectors are great when you have millions of features, but most of them are 0. Bottom line. You have millions of features, most of them are 0. We like sparse vectors for big data. But these are different data types you're going to see. You know, vectors.norm, let's just take the norm of a vector. We don't need to worry too much about that. We have sparse vector in here. Labeled point, do you guys remember what labeled point was? That's a feature and its label. And what are we going to use that for? Training. Because you're going to give us a feature, X, and the right result, Y, and I'm going to learn the model. So we're going to give it a bunch of labeled points to learn the model. Very good. Ratings are used by recommendation systems. And then last but not least, we learned about data frames. So we're going to skip past all of this and jump straight into ETL k-means right now. Now the ETL k-means is broken up into parts, and we're going to actually let you guys tackle this a little bit, but I'm going to go over part 1 right now. So when you open this up, you're going to go either to Python or Scala, and you're going to notice it's broken into parts, and the idea here being that even if you get stuck on part 1, later on you can jump ahead to part 2 and you'll run the answer from part 1. So it ensures nobody gets left behind and allows us to run a little bit faster and do more interesting models. So to begin with, we're going to start with MLlib. Remember, MLlib is the RDD-based way of doing things, because we want you to be familiar with both MLlib and ML pipelines as a result of this class. So the very first thing we have to do is load the data. So fortunately, our data is right here under Mount ML class. And how many of you guys have worked with the iris data set at some point in your career? Yes. If you're a data scientist, this is like the most famous k-means example, because they learn all these features about these flowers, and then they say, can we cluster them? And lo and behold, it comes out to be species, just by clustering. It's like, we don't even tell it how many, we tell it how many k-means there is, but we don't necessarily tell it how many species there should be, or what the species are. We don't give it any training data, and it still learns this. All right, so the first thing we're going to do is there's a nice little utility here called MLutils that comes inside of MLlib. And we're just going to say, load for me this path, the iris data, into at least 20 partitions, and let's cache it. And so I'm just going to run this cell. You're welcome to run this cell. I would have you guys open the student version of the notebook. For now, I have the answer version just so that I can clue you in on what's expected on this lab. We are going to be building machine learning models. Now, how many of you guys said you had to reattach to your cluster? So we're running on Community Edition. Remember, Community Edition has us all pooled into a big farm. So there's two versions of Databricks. There's Community Edition, where you're running on a shared pool of resources, and you pay for extra power that you want. And then there's Enterprise version, where you have dedicated servers. We're using the one that's a pool, so after an hour of inactivity, shuts down your cluster. So you may have to wait for your cluster to boot up again. So while we're waiting, let's talk a little bit more about this lab. So first thing we're going to be able to do is just look at the first few lines of this data set, and what you're going to notice is that it's a comma-separated values. So we're going to have to actually parse this, and we want to convert it into a beautiful data frame. So this is a great example. I'm reading a text file that has no structure initially. Well, it may have structure, but it's not visible. I'm just reading it as a text file. And what I'm going to do is use some RDD operations like map partitions to try and get it into a nice little data frame. So let's see how we're doing here. All right. So notice that the file has a label point. This is the prediction, and this is the feature. Can everybody see the screen okay? Did everybody get to run the cell in your notebook? Perfect. So we now just say, show me what was actually in the file. If you were to look at the raw file, notice it's prediction, followed by sparse vector notation. You guys notice the sparse vector, index, colon, value, index, colon, value, index, colon, value, index, colon, value. This works when you have millions of features. Most of them are 0. And we just read that file. But by using this little utility here, it's able to parse them into label points for us, which is really, really handy. So that gives us now our iris RDD. We could take a quick look and see how this data is stored. So let's just take a look at how many things are in each partition. Notice that partition 0 has 8 flowers. Partition 1 has 7 flowers. Partition 2 has 8 flowers, and so on. So not all the partitions are necessarily going to be the same size. It depends on the underlying file storage format. So in Parquet, it's not necessarily the case that each partition is going to have exactly the same number of items. You could always rebalance them later if you chose. It's based on the underlying storage technology. Now you guys are looking at map partitions with index. What the heck is that? Or irsrdd.glom. What the heck is that? Let's just look at this another way. iris.glom.take1 or take2. Notice what this does is it makes a list out of everything that's in the first partition. See how there's a list of lists? Takes everything in the first partition and makes it a list. Everything in the second partition and makes it a list. So at that point, I could go glom.map, given a list, give me the length of that list, please. And I know L is a bad name, so a list, length of a list. And notice I get lengths of each of my partitions. And so I'll just get the length of all of my partitions here. This is doing normal RDD transformations and actions. So I've got a list of lists. I grab the length of each list, and I can quickly see how many flowers are in each partition. This is interesting if you want to get insights into what's under the hood. But really, we'd like to not deal with it at this level. We'd like to just start dealing with it as a data frame. So how do we convert an RDD of objects into a data frame? So we've read them in as labeled points. Let's convert this to a data frame. And I'm going to use display to make it pretty. Notice I have a feature and a label. It figured out it was called features because it looked at label points attributes and saw it had an attribute called feature and it saw it had a field called label. Now, what is this mess? Anybody? This is a sparse vector. So let's take a look here. All right, so this is a sparse vector. So at index 0 is this number. At index 1 is this number. At index 2 and 3 are these last two numbers. So it doesn't display terribly pretty, but this is meant for when you have millions and millions of features, in which case printing them all out with all those zeros would be incredibly painful. All right, so this is our data set. We could also just call take 5 and see it printed out this way, which is a little bit more readable in my book. And run it again. We can go dataframe.show, and notice that I get it in a tabular format, just like we did with display. Has everybody been able to run these so far? I'm going to give you 30 seconds right now to run up to irisdataframe.show. Tell me that you've seen the data, and then we're going to start training our model. Remember how to signal to me that you're ready to move on? Dun, 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 dun. So look at your neighbor, check and see if they don't have their flag, ask them if you can help them. I look for at least 80% of the room to have a flag up. We're doing pretty good there. Does anybody need just another 30 seconds? Maybe your cluster's coming up, in which case you can catch up later. Is anybody waiting on their cluster to start? Yeah, just give it a little bit of time. It'll start. We won't wait on your cluster, though, because Amazon takes a little while to spin up. All right, so we've got our data frame. And notice that our data frame, in fact, has a schema. Notice that a feature is a vector object, and the label is a double. And how were we able to convert labeled points to rows? It's simply looked at. So this is a really good question. Remember, it was a list of label point objects, and they simply became data frames. And this is beautiful because if you were to take a look here, what if I just made a person object? And I make a data frame of people. Notice it's able to do what's called schema inferencing. It looks at the schema of the object and creates a data frame schema for us. Pretty cool feature. So it can work with any kind of object, not just labeled points, and convert them into data frames. And once they're data frames, they now are able to make use of native memory, unlike with RDDs. Let me skip ahead a little bit. If we were to look at our person data frame as well, you could see that in fact it has a schema. I'm going to skip ahead a little bit. But notice it even inferred that it was a long, not a string. Pretty smart, just by looking at the data in our objects. This is known as schema inferencing, and it's your friend. I'm going to skip ahead a little bit now. We want to get to the point where we're transforming our iris data. So has everybody scrolled down to where we talk about transform the data? Well, Lead's here to help answer any questions you guys throw our way as well. In fact, if you're wanting, you could go and you can either steal my laptop and be answering questions while they're tweeting them live. I just need to turn off my screensaver. Well, we'll do that during break because I have to turn off my lock screen. Well, Lee was kind enough to give me his Windows machine, so I stopped fighting the Mac. I failed. Oh, everybody's groaning. All right. Now, your first lab. Dun, 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 should you choose to accept it. Dun, 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 dun. Here you have your iris data set. So you've got your features, and you've got a column called label. And if you look at our labels, go back up again, notice that our labels were starting with the number 1 instead of the number 0. We'd like our labels to start at 0 so that we don't have a y-intercept. It's actually not all that important. We can totally have a y-intercept in our training. But just for the sake of it, we're going to go ahead and process our data to subtract 1 from all of the labels. So you are going to have to write a query to process your data frame and to subtract the number 1. There are many ways you can do it. I'm not going to leave the solution on the screen, but you could do a select statement. Now here's what's really important. Notice I imported the column function. I could either use the column function, or I could actually just go iris data frame bracket label. If you're using Scala, you can use the $ syntax. And I'm just going to subtract 1 from it and call that result label. And notice that now my labels start at 0. Those of you who feel like it, you're welcome to try it a different way. You could go iris dataframe.register temp table, iris, and then you can then go and you could even use %SQL if you wanted to. %SQL, select features, comma, label -1 as label from iris. And there you have it. The labels now start at 0. So you guys are welcome to tackle this lab however you would like. What's important, though, is that you actually save it as a new data frame called iris_df0index. So notice me using %SQL, it was only good for displaying results. If I actually wanted to save it as a new data frame, I have to go SQL context.sql so that it's now Python code instead of SQL code and embedded in a string. And then I can go display iris_df0index. You guys are welcome to do it either way. Take your name tag off, put it back as soon as you've solved that lab. You guys should have a nice to-do. If you have trouble with Scala, I can help you out. Waleed can help you out with Scala, so can the TAs. I've just got one possible solution. You guys are welcome to use any variation you'd like. So here's what I'm going to do. Hide result. And I'm going to talk about something interesting in this answer about why, like if you look at this one, why do they have to use the column function? I'm going to talk about that in a moment. Just want everybody to get one of these two and put your name tag up. You're welcome to use either one. You're welcome to steal my answer or figure it out on your own. There we go. Sorry, guys. Remember when you do register temp table, not actually saving anything to disk whatsoever. It's just making an alias that you can use in a SQL string. So the term temp table is actually a terrible name. We suggested to the engineers they rename it register alias or something like that. It's more meaningful, but they're like, well, alias also has a meaning in the database. You just can't win. All right, guys, I'm going to go back to doing a solution here for you. I'm going to walk you through this, and then we're going to move on because I've got the majority of you guys with this lab fairly quick. So first of all, did you find typing it in was helpful to you? There's some interesting questions that came up, and I want to cover them. So number one, let's look at this. Could I have just selected features and labels? Label, singular. Absolutely, I could just select feature and label. Now, some people said, all right, I did feature and label, but now I want to subtract the number 1 from label. Does this work? You would want it to work, but it complains that label is a string, and you can't subtract an integer from a string. How many of you guys got that error? Now, so what we've got to do, see, if we were to print out the type of label, it's a string. I want to get an object that actually represents the column so that I can do math on the column. So there's two ways I can do this. I could call the column function that we just imported. And notice now I get a column object. And on a column object, I'm allowed to do subtraction. Those of you who are in Scala can use the $sign. Unfortunately, the $sign is not a legal variable name in Python, so you're stuck calling it call. Now, the other way to do it, like SQL, you could say select label, or you could give it the table name .label. So I could go irisdf and that too returns a column object. Now it's clear which table it comes from, and I'm bumping up a lot on my mic. Is there something I should be doing different? There we go. I think that might be better. We'll see. There we go. Let's see if that doesn't. Oh, good. You got an actual. I just moved it down. We'll try it one more time. You can bring me the hand mic if that doesn't work. So here we go. irisdf label gives me a column object. Now, those of you who are in Scala, remember you could use the $sign syntax in Scala. Where's the insert key? Those of you who are in Scala, you have the annoyance that you can't mix strings and column objects because it's a strongly typed language. Python is smart enough that I can actually select some of these guys as strings and others of these as column objects, which is really nice. And the other nice thing I can do, given that I'm in Python, is I could even go irisdf.label and treat it like a field. Oh. irisdf.label -1. There we go. Now, the last thing is, if you look at this, notice what's the name of this column over here? Label -1, right? Boo. Let's fix that. How do I change the name of my column? Alias. Now in Scala, you're allowed to go as. In Python, as is a reserved word. So we got to use alias, and I can call it label. And now we're happy. So that was a relatively straightforward lab. Wow. Oh, it's the plug. It's the plug doing it. Here we go. That might have fixed it. I just moved the position on my belt. Go ahead and give me the hand mic just in case. All right, so now you want to make sure that your result works. So here's the way we're going to do our labs. Notice this little test helper. It's going to make sure that you did it correct. So go ahead and run your test function, and it should pass. Now, when you look at this, notice it's a sparse vector of 4 values. Here it's a sparse vector of 4 values as well. It just so happens that value number 1 was 0. For the purposes of visualization, we're going to just trim, just to make life easier about what k-means is doing, it helps to be in 2 dimensions instead of 4. So what we'd like to do is drop 2 of the dimensions. So given a vector of 4 dimensions, I'm just going to truncate it to be a vector of 2 dimensions. How do I do that? To do that, we're going to use a feature known as a UDF. And I'm going to show it to you, and then I'm going to let you guys try to code it in here. So notice, first of all, I got to import from PySpark SQL functions, I'm going to import the UDF function that allows me to define user-defined types. And now I'm going to make a little helper function here that says define sparse or reduce to 2D. So given a sparse vector, what I want to do is make a new dense vector and only keep the first 2 elements. So remember, I'm going to go vectors.dense. This makes a dense vector. And I give it my sparse vector. But I only want the first 2 columns. So let's take our sparse vector, convert it into an array, and I want columns 0 and 1, but not 2. And this is the way you do that in Python. And now I have a vector. So let's test this really quickly. I'm going to do this up in a separate cell just to show you what the code is doing. So let's test it out. So I have vectors.sparse 0, 0, 1, 2. You don't have to type all this in. I'm just showing you what we're creating here. Come on, print SV. I got to import the vectors type. A sparse vector is a little annoying. I want column 1 and 2 to be the values 3 and 4. And I want it to be of size 5. Making an ugly sparse vector. This was the earlier lab we skipped. I'm just doing it as a demo. So here I have a sparse vector of size 5 where these items have these values. And now I want to convert it into a dense vector. So all I have to do is go dense vector equals reduce to 2D sparse vector. And let's print that instead. And just make my D capital. Oh, and I got to return it. And there we go. I got 0 and 3. So it's a really simple function that's just keeping the first two items. I'm going to go ahead and give you that function to make life easy. But now, down here, we want to define, so I'm going to just copy paste this down to the cell below now that I've explained the code. And I want to make a user-defined function. So I'm going to call this my first two features UDF is what I like to use. In this case, we're just going to call it first two features because of the way the lab is, but we're defining a user-defined function. We give it the name of the function we want to create. This is the function we want to use. And what's the return type? The return type is a vector user-defined type. So I'm making a function that I can now use in a select statement. It's a function that I can now call in a select statement. I could even have a little bit more fun if I really wanted to and go SQL context dot register. Is it register UDF? SQL context dot UDF and give it a name. Two features. And I could call it from SQL at that point. So I'm able to actually call it from SQL if I wanted to, or I could call it using the Python API. What is it? UDF registration object not callable. I'll work on that one later. Can you check my syntax here? What am I missing? I wanted to get registered as a named UDF for purposes of calling SQL. We have to check the API. I thought it was register UDF. It is register UDF. Thank you. And now I could actually call it in my SQL as well for those of you who wanted to use SQL. So here you could write your code one of two ways. You could go iris data frame with a 0 index, or I could go SQL context.SQL, select, and then I call two features of features as features and label from iris. You could do it either way. I'll let you guys choose which of the two ways you want to do it. You can use either the SQL style or the data frame style. Notice now I only have two features, and they're a dense vector. Do you guys need me to separate the two sets of code? Go ahead and do it now. While you're working on this, I'll separate the two ways of doing it. I'd like you guys to try just one of the two ways is fine. I just know some of you guys prefer SQL, some of you guys prefer the other. I've deliberately avoided using a lambda expression to make your life a little bit easier. But you don't have to use, you could use a lambda expression if you want. Go ahead and do your work right now to try to convert it to a sparse vector. And put your name tag there. This is version 1. And now I'm going to make version 2 down here. You can call either of these two versions. You don't have to type my screen. I want you to try and actually code this yourself. My screen is here to just help keep things moving along. You're going to need user-defined functions during your data science. So you guys are welcome to copy-paste from the solutions if you get behind it all. This is just step one. And you can test it. It would give you an error if it didn't pass. All right, so I think most people finished. Here's what we're going to do next. This was just step one of the lab. Notice it was a lot of data frames mumbo jumbo, but it's because it's necessary to do our ETL. So now, let's go to step two. Go ahead and open up ETL k-means part 2. By the way, when is the next break? Is anybody tracking breaks? I think we're good for a little bit longer. And in part 2, what we want to do is save our data set out to a file. We're going to save our data set out to a file. Let's see here. How many people are still working on the previous one? You're in luck. You'll be able to work on your previous one during break because to go to part 2, you do not need to have finished part 1. Sorry, I'm cracking the whip just a little bit. I want to make sure we get through a couple of other interesting examples here. So we're now in part 2. Notice part 2 will run the solutions to part 1. If you come up here to the top, run solutions to part 1. Question? Oh, the path is wrong. Look at that. All right, so the correct path would be labs data science.
You have to remove the space from data science. You have to remove the space from data science folder as well because they run those like 6 spaces.
Really?
Oh, you can put double quotes, yes.
Data science. And then we need to put quotes around this whole thing. Attach and run. Good catch. I missed that yesterday. And it just runs the previous answers. So let me leave up that top part. Percent run. Let me know when you're done with the percent run. Labs, data science. Put your flag up as soon as you got it to run. Has anybody not got that to run? Let me ask that. Okay, I'm going to give you another 30 seconds because this is critical. All right, so now we're going to look at just, and I'm going to do this, I'm going to change up the strategy a little bit because I want to make sure we get to training actual models and a variety of different types of models. So I'm going to change my tack just a little bit for the pacing purposes. So what we have right now is we finished running all of that work and we now got to part 2, I believe. Here we go, part 2. We look at our first row. Notice we've got a nice dense vector to work with just 2 features. And what I'd like to do, I'm going to skip ahead a little bit, is I'd like to save this new data frame out to disk for fast, quick access. So how are we going to do that? Well, we're going to just generate a nice random number using UUID. This is less essential since you guys all have your own private instance of Databricks. But we're just going to write it out to a temporary folder right now in Parquet format. So take a look at how that works. Iris, 2 features, .write. I can choose whether I want to overwrite or not. And then how am I going to write it? I'm going to write it in Parquet. And I give it a file name. You could put your name in here for the file name if you wanted to. There's no need to do fancy formats. I wouldn't bother changing it. But it's just trying to make a unique file name so that 2 people weren't clobbering each other. We actually don't have that problem here in class because every person has a private workspace. But this is sometimes done in a class where we have a shared workspace, so we were using a unique ID. So go ahead and just run that line, complete with the unique ID that was in there. And it's actually writing our data frame back out to disk in a highly efficient Parquet format, which is very efficient in reads. And we can look at it. Go ahead and run the next cell and look at it. Notice that my Parquet file is a bunch of zipped up partitions. It's just a bunch of zipped up partitions. I just ran dbutils file system ls. It's a bunch of zipped up partitions. Incidentally, we could have actually had fun and gone just file system list. We could have done that. I'm not going to bother, but we could have. All right, now moving down. We can actually overwrite. We can actually save our 0 index version of it as well to a partition. Go ahead and run that. And you should now be at the k-means section. And this is where we're going to do the data science. And this is really what I'm trying to drive us towards, is more and more of the data science here. So I apologize it's taken us this long to get to the data science, but I am determined you're going to get a lot of data science today. Is anybody still catching up? Raise your hand if you're still catching up. Awesome. Oh, 1 person. Okay, can a TA make sure she's caught up? TA? Second row, second seat. Is anybody else looking for some help from a TA? Say again? So first 4 features meant it was a 4-feature data set. We downsampled it to a 2-feature data set. That's all. We just saved them both off to disk. That's all it is. We wanted the 2-feature data set because I'm going to do some plotting and visualizations later to explain k-means, and it helps to be in only 2 dimensions. The original data set was 4 features. The original data set was 4 features. All right, guys. So at this point, let's do a k-means training. Let's do a k-means training. So here we have it. I'm going to create a new k-means clustering estimator. Oops, I'll use my screen pointer so I'm not messing up the camera. Come on. There we go. I'm going to import k-means. And I'm going to say I want 3 clusters. So I'm guessing I've got 3 different types of irises. I'm going to allow my algorithm to iterate at most 20 times. And it's actually using a smart algorithm called k-means parallel to do some smart initialization. So those of you who remember k-means, classic k-means picks 3 random points and moves them around. There are some algorithms, that was k-means plus plus, that used a smarter version of an initial guess. And then there's a parallel one. So we're just telling it, do 1 iteration to get a better initial guess, then iterate 20 times. Now, what on earth is this set seed about? That's my random number generator. It could be any seed I want. Question? Oh, it was rhetorical ask. Rhetorical ask. Why set the seed? And it's very simple. If one machine goes down, and I got to reproduce this, and I have a random number in there, then when I reproduce it, it's going to reproduce differently. So by setting the seed to any seed at all, 42 is a good number, by setting the seed to any seed at all, I guarantee some reproducibility in the event that a machine dies and I had to recreate the data. So I run this. I create a new k-means initializer, and I say I want to fit my data set. I want to fit my data set. And now that I fit my data set with a model, I want to look at my original data and figure out which cluster it got put into. So let's try this out. I'm just going to run this code briefly, and then I'm going to let you guys type in some of it. No, I don't want the centers. I want to display transformed. Notice now I've got my data set, a label, and a predicted label. And it's actually pretty good, except for the fact that, well, nobody decides what is going to be number 1, what is going to be number 2, and what is going to be number 3, right? These are arbitrary labels. So notice, though, that most things that were in the same group before are still in the same group afterwards. This is pretty good. Most things that were in the same group before are in the same group afterwards. Now, look at this guy. This guy was technically part of the first group, but he got thrown into a second group. So I did get a couple of errors. Does that make sense, by the way, why the 0 and the 1 are not the same here? It would just be like calling this team 0. And then over here, it was like team beta. They just changed the name. But its bottom line is I got 3 groups either way. 0, 1, and 2. It's just how we number them is what's changed. The point is that all the 1s are supposed to be in the same group. Question, yeah? Oh, you want to be able to look at the accuracy with the confusion matrix, you said? So not for the confusion matrix itself, but you can get, actually, Waleed, I don't believe there's a confusion matrix. Correct me if I'm wrong. There's not a confusion matrix itself, but what you can do is actually do some analysis, and we're going to do that in the next lab to see the accuracy and to compute the accuracy. But it's not going to be as detailed as a confusion matrix for one simple reason. The confusion matrix requires a closed form solution. So it doesn't scale to big data versus the iterative algorithm. Actually, that's not entirely true. But the confusion, because even the small data version is iterating, but calculating the confusion matrix adds overhead. And so it's going to affect the performance a little bit. Yeah, you would just compute it afterwards.
Use the binary, the multi-class evaluator has the confusion matrix. There's an evaluator class available in ULM.
So we can do post-processing to get your confusion matrix. We're going to see that actually in the next slide too. Not the confusion matrix specifically, but we'll be able to do some of that post-processing, evaluating the quality of our result. Let's go ahead and continue on here. I'm going to let everybody code this up though, because this is the most important part, what you've been waiting for. You guys want to go ahead and do a k-means clustering on our data frames data. Notice most of the work was data frames, and just a little bit of the work was using the actual MLlib libraries, or Spark ML library. Go ahead and code this in. Actually, for now, would you rather code this in or would you rather run the solution? How many of you guys would like to type this in? How many would rather run the solution? Run the solution. As long as it makes sense to you. I don't think there's a lot of value just typing this in. There's a huge amount of value getting you comfortable using the data frames, though. All right, did everybody get a chance to run that? Now we want to get to the really interesting, juicy part. And when is break, by the way? I don't want to miss a break. I think it's still another half an hour, if I'm not mistaken. Now we want to get to the juicy part and see, how did we do? How did we do? This is the real emphasis in data science, right? Calling a k-means algorithm is easy. Analyzing what happened, that's the good stuff. So let's get everybody back together again. Ready for a short joke? Just to bring your heads back in, because you're welcome to stand up during the joke and stretch. Just to keep your head clear. I do jokes purely to get you out of your email. So there's one rule of jokes. No web, no email. And you have to stop the old lab too. All right, let's see here. This time, an engineer dies and goes to heaven, but it's not just any engineer. It's Bill Gates. And he gets up to heaven, and he goes up to the angel, and the angel says, "Ah, Mr. Gates, we have been expecting you. The trouble is, we are having quite the debate about what to do with you. So we've decided we're going to let you decide." So Bill says, this sounds really good, but I've never died before. How do I know what heaven and hell are like? The angel says, "Fair question. I tell you up. We'll show you." So he takes Bill up to heaven, and you see all these programmers sitting there blissfully in prayer, sitting on their clouds. A few of them are even playing Halo. And Bill's like, "All right, I've seen heaven. Show me hell." He gets down to hell, and there is he's taking pictures. This is going to be crazy. There's this beach party going on. Sin, debauchery, you name it is happening at this party. And Bill's like, whoa. Who would have thought heaven was such a happening place? And the angel says, "Well, Bill, it's time for you to decide." Bill says, "I've been bad. I've been very, very bad. Yeah, I did some good stuff with my charity work and all, but I invented Windows. Blue screen of death. Then there's that thing called Office. Yeah, okay, it's a blue screen of death. That really does it." So the angel's like, "So where do you choose?" He says, I choose hell. I definitely deserve to go to hell after that." And he just says, "Okay," snaps his fingers. And there's Bill Gates in hell, waist deep in lava, writhing in agony. And he says, "What happened? Where's the beach party? Where are all the women?" I feel like a photo shoot. "Where are all the women?" The angel says, Bill, surely you of all people would understand. That was the demo. Okay. Hopefully I don't get in trouble for telling that joke in a recorded video. All right, ETL and k-means. So let's go to part 3 here, because part 3 is really the interesting part, and we're going to do several other labs. I want to try to keep a good pace going here. So first thing I'm going to do is run part 2. And then I come here to part 3. And remember, what we found, oops, wait for that to finish running. Oh, I have to update my path again. Sorry, guys. That is labs, data space, science, and in quotes. Oh, I see your answers is now going to call the previous answers from 1, go back. Yeah, that's going to be a bit of a pain. What is it? Labs, data science. I'm going to go ahead and run it, and then I'll let you guys work out the pathing issue. I apologize for not catching the path issue yesterday. I was testing all the labs out, but I didn't see this issue. There is actually a solution to this problem. If you go into ETL k-means under Python, there is a version of this called answers without any parts. Why don't we do that? Go to the version called answers without any parts at all and run that. Let's go to the version called answers without any parts, have everybody run it. The nice thing about parts is that it lets you kind of code along. The downside is that inclusion there. No, we went to the one that was not called part 2. It's just called 2 ETL k-means answers. It is the cumulated answers across all 3 parts in one notebook. And the irony is, yesterday I was going, should I delete that and just have everybody work with parts? I'm glad I didn't. I left it there just in case. So now we go to part 3. I'm scrolling down to part 3. And what I want to point out is that we've learned some centroids, but what exactly does this mean? So I thought we would do some visualizations. So go ahead and scroll down to k-means visualized. K-means visualized. Everybody there? In the answers? Give you a moment. Well, no, I just ran the whole notebook. I opened up k-means, ETL, k-means, underscore, underscore, answers, and ran the entire notebook. How do you run all? There's a button at the very top called Run All. Right at the top, there's a button called Run All. While everybody's busy running all, I'm going to show you the visualizations here, and then I'll walk you through the code that produced these visualizations. But I really want us to visualize what just happened. So notice, oops, I'll stay over on my computer for the recording. Notice what I have right here. Is a centroid of a cluster. So what it's done is it's basically tried to find the 3 centers that made sure that distances were as close to a center as possible based on the 2 features we were evaluating. So notice all of these irises in red. The red color means that this is what it actually is. And we'd have to look up what species of iris it is. But let's just say it was the blue iris. Or better yet, the red iris. It was an iris that was red colored. Let's pretend. So notice all the red ones were actually the red colored irises. And it was able to learn most of them fairly effectively by just saying it was the closest to this glop of points here. Just think about a bird. You could tell the bird spends a lot of time in this area. And then we could tell that there's another natural cluster right here where the bird spends a lot of time in this area. And another natural cluster right here where the bird spent a lot of time in this area. Except in this case, these are irises that divide up neatly into 3 categories. Except some things are going to accidentally get categorized in the wrong place, and you can see that in our picture here. There's a few grays in the middle of my yellows, there's a few reds in the middle of my yellows, etc. But I did a pretty good job identifying the species of flower. And if I were to go down further and do some plotting, you can actually see what happens over time. So starting out, it picked the center right here. It picked the center here, here, and here. And then notice the next iteration, what it does is it says, hey, this guy, if all of these guys here are red, maybe I should move my center to the center of the reds. If these guys are all yellow, maybe I should, well, that's actually pretty good. It's grouped really nicely. But this gray, I'm going to move it just a little bit over. I'm going to move this guy just a little bit over. And everybody moves just a little bit. And you could see it over a couple of iterations. And if I were to superimpose these plots, scrolling down, you can see the gradual migration of our centers from here to here to here to here as I'm trying to do my k-means clustering. It's just trying to choose better and better clusters each time. Now this is really cool visualization. How did I do this? How did I achieve this kind of visualization to give me this kind of analysis? Let's take a look. So we scroll up, and let's take a look at our code, k-means visualized. So first of all, I went ahead and just grabbed a copy of the model, one copy of the model for 0 iterations, one copy after 2, one copy after 4, 7, 10, and 20. And I basically just reran the training so that you could see that plot line. Does that code make sense? I'm just looping through and adding a new model each time, and I'm grabbing those centers. And then take a look at this code. This code has absolutely nothing to do with Spark whatsoever. What is this code if it has nothing to do with Spark? It's matplotlib. It's a standard open source Python plotting library. So I'm not going to bother reading you through it because this is just standard matplotlib plotting. If you've been working with Python for any length of time, you've had to do plotting. There's absolutely no Python in here whatsoever, or excuse me, no Spark in this code whatsoever, but I'm using NumPy and matplotlib. And the one place you see an actual bit of Spark will be when I go to just call that function and display it, and I'll show you that in a minute. Here we go. I'm now going to actually try to do that plotting. So I'm going to prepare my subplot. And let's see here. Where's my original data? So this is my original data, iris2features.collect. So now I've got my data. I'm going to try to grab my features and my labels out of that. So I now have features and labels separated. I do a bunch of plotting, and then notice once I've got my plot called figure, I'm just called display figure. And there it is. Great question. So if I did fig.show, I'm running on a headless Linux box. So it says here, non-GUI backend. Now that always annoyed me because I liked my code to be able to run well in Databricks and offline in Databricks. So here's what I tend to do, is I tend to go fig.show equals lambda, lambda given self, display self. And now I can call fig.show. So I override what fig.show does. That should have worked. No, that should have worked. In any case, I'll play with that over after break, but I actually often will, I have a little library that I run that will make fig.show call display. Say again? Not in this notebook. There's not like an inline mode. It'd be really nice. Does IPython notebook actually do that? Oh, that's pretty cool. So no, here you call display. That's the short answer there. Break time, perfect. So I'm going to scroll a little bit down to the last significant part here. No, we're not going to use mllib instead. That's not worth it. Did want to see if we had an evaluator in here. Nope, so during break, I'll pull up an example of an evaluator. We're going to do another example after break of a different type. We're going to do a logistics pipeline for logistics regression. Before we do a break, I really want to get a sense of how we could tweak the class for your needs here. I know you guys are really interested in seeing all the data science features in Spark. We spent a lot of time on some of the data frames features, which are really essential, but I know you want to see more of the data science features. So I really wanted to get a sense of how we could tailor the last 2 hours to your needs here. So how many of you guys really enjoy going, like this last example where we did k-means? How many of you guys really enjoyed the coding part of it as well? The little bit of coding mixed in? Pretty good. So if I did more of what we did this last hour, will that be really good for you guys? Okay, good. I was trying to pivot based on some of the sense of the room I got during lunch, and I want to continue to pivot to really give you guys the value of the class. I apologize, the data frames, like a couple of people said, yeah, we already knew data frames. So I definitely understand that part. But you can see everything to do with matplotlib builds on top of data frames. Or excuse me, everything to do with SparkML has to do with data frames. And data frames is how you do your featurization for the most part. All right, guys, I'm going to see you in 15 minutes. Question here.
Can you keep 10 minutes to explain data?
All right, how many of you guys have kids? All right, so here's a joke for the kids when you take home to your families. So this is corny, but remember, corny jokes clear your mind better than good jokes because they just wipe your brain clean. So here we go. A chicken walks into a library, goes up to the librarian's desk and says, "Bark." Librarian just looks at this chicken. Chicken says, "Bark." Librarian says, "You want a book?" Chicken says, "Bark." So the librarian shrugs, goes over to the desk, picks up a book, hands it to the chicken. Chicken tucks it under its wing and walks out the door. This happens to be a MacBook. So hour goes past. Chicken comes back into the library, straight up to the librarian's desk and says, "Bark, bark." Librarian says, "You want 2 books?" "Bark, bark." Librarian shrugs, goes over to the bookshelf, picks up 2 books, hands them to the chicken. Chicken tucks it under its wing and walks out the door. Another hour goes by, and back comes this chicken. "Bark, bark, bark." "You want 3 books?" Librarian sighs, goes over to the bookshelf, picks up 3 books, hands them to the chicken. Chicken tucks it under its wing and walks out the door. Well, around this time, the librarian's starting to get curious. What is the chicken doing with all these books? So the librarian decides to follow the chicken out the door, down the corner, down to the pond. And there's the chicken, holding up each book to a frog. And every time the chicken holds up a book, the frog says, "Read it. Read it." Okay. Take that one home to your kids and try it out. My nephew loves that one because his mom's a librarian and his favorite stuffed animal is a frog. So, all right. Yeah, you guys got to live with the fact that jokes have to be corporate safe, especially when on video. So everybody knows that good jokes aren't quite so corporate safe. All right. Somebody had asked me, hey, Doug, can you tell me more about data sets during break? And there's a really good presentation that we just did on data sets. It's only an hour long, actually 48 minutes, comparing RDDs, data frames, and data sets. But I thought I would give you the really short description right now. So take a look at this code example. We're going to read a JSON file. Now what I've got is a data frame full of rows. A data frame full of rows. But I happen to know that this JSON file has a name that's a string and an age that's a long. So here's a case class, or the same as a name tuple in Python. Ish, same-ish. As a name tuple in Python. So I'd really like to treat it as a person object and be strongly typed. So notice with data sets, all you have to do is go dataframe.as and you give it the type. And now whenever you work with it, it'll be that type of object. Now, the Scala people who love their strongly typed languages absolutely love this, or statically typed languages, I should say. Absolutely love this because now their compiler gives them code completion and a bunch of other things. Python benefits a little bit less from it. It's not as essential to Python users, but they've unified the idea of a data frame and a data set starting in Spark 2.0. In Spark 2.0, a data frame is really an alias for, data set of row. Now that is a non-backwards compatible change, so that's one of those things that you'll have to be aware of when you go to Spark 2.0. They basically realized that RDDs were great from an architecture standpoint, but were painful for the user. Data frames were better, but you lost type safety. So they've come up with one API to rule them all, the Dataset API. Strongly typed, declarative, can do queries that are optimized by catalysts, and when you really need to, you can still call map and flat map and all the RDD operations. So it's no more data frames here, RDDs there, data sets there. It's just one nice clean API. Now the RDDs are still there in 2.0. They're just under the hood. So if you got tired of having too many APIs, Spark 2.0 is your friend.
When you say under the hood, do you mean that you can't actually create RDD anymore?
You can create RDD still. The API will still exist. But data sets, of course, are going to compile into, with the Catalyst Optimizer, into RDDs. But the intent is that you shouldn't need to work at the RDD level except for rare circumstances where you want manual control. The point is to make life easy. You know, the whole mantra, big data should be easy. Here's an example, though, of what I mean by unifying data sets with RDDs. Take a look here. If I was doing the RDD world, I would have had to group by the lowercase and then do a map operation to figure out how big it is. With data sets, I could do a group by, take the item and make it lowercase, and then call count. A little bit cleaner. So it's less typing and tends to execute faster than RDDs because of the use of native memory and the Catalyst Optimizer. So there's a really great presentation on it. I'm not going to go into any more details. Brian Clapper is an excellent speaker, so I highly recommend it. And what was the name of it? It was called RDDs, Data Frames, and Data Sets in Apache Spark. I sure could put the link into the document. Great suggestion. Picture taking was getting very distracting. I see your comment. All right, question. Where can I get the presentation on data sets? Answer. Here. Some other people were asking what were the features in that example we just did. So we decided to work with sepal width and sepal length. So one of the reasons we had false positives there, or false groupings, is because in our 2D version we didn't get petal width and petal length. And some of the people said, you know, why don't you use principal component analysis to reduce the vectors rather than doing, like, reduce dimensionality rather than just throwing out 2. That's absolutely the case. We could have used principal components, but then it's unclear exactly which feature we were looking at. So the only reason we even reduced to 2 dimensions was to make that plot work at the end. All right, so with that said, by the way, TAs, let me know if there's specific questions that look really interesting that people would like covered. Maybe make them bold. I'll ask the TAs to maybe make them red or some other color so that I know which questions to make sure people are most interested in, and feel free to upvote them. Meanwhile, I'm going to go into more detail on the next topic, which is pipeline and logistics regression. Oops, what did I do? Pipeline and logistics regression. There we go. Python. And I'm just going to be easy. I'm going to run the whole answers notebook for the moment. I am going to have you guys do some coding in the student notebooks. But for the time being, I'm just going to run the entire answers notebook. Zoom out. Actually, I won't run it until I need it. So let's zoom in. And this time around, we're going to do logistic regression to try to do a better classification. So remember, linear regression produces a nice numerical score. Like, what percentage likelihood is it spam or not spam? Some nice linear number. How interesting is the log file? Logistic regression is kind of an approximation of the step function. And by being a logistics curve rather than a step function, it happens to have slightly better mathematical properties for our formulas. So logistics regression we're going to use to do classification. Is it this kind of flower? Yes or no? Is it this kind of flower? Yes or no? Is it this kind of flower? Yes or no? So we're going to read the same data set as before, our 2 features Parquet file, which, hey, we happen to have already saved to Parquet earlier. We might as well make sure it's cached. So we're going to read the Parquet file. Now notice, if I'm reading the Parquet file again, I'm making a new copy of that data frame in memory. I better set the cache flag. It's not smart enough to go, oh, you've read that file before, I already have it cached. No. The cache flag is on the copy you just read. So I do need to call cache. And then let's just take a quick look at the file. So I'm just going to do a quick operation where I'm going to take each feature and get its repr. That is, I'm going to try to print it out like an object. This is just Python code to make it print pretty, okay? I could just as easily have called take2 and not put in the pretty code. It would look pretty close. It just wouldn't be as well featured. Iris 2 features dot take2. It's actually pretty much the same. I don't even see why I would have needed to do this fancy join code. Iris 2 features dot take2 looks pretty good to me. And of course, I could print it as a beautiful HTML table using the notebook proprietary features. And I don't necessarily think that looked any prettier because it's got the sparse vector notation. So in this particular case, I liked it up here a little bit better. Now, what we want to do is prepare our features. We want to prepare the data. So in this type of round, remember, we've got our dense vectors. And what do we want to do with it? We want to call this lit function. Let's take a look at it here. Functions.lit. Let's take a look at what that code actually does. So I'm going to go help pyspark.sql.functions.lit. And since I haven't imported it yet, here it is. creates a class using a column using a literal value. So I can add a new column, and I'm converting it to a literal value. So like lit1 would mean this is the number 1. Let's take a look at an example usage of this. So here, I'm going to add a column. I'm going to add a new column to my data frame. Let's take a look at my data frame again up here. Notice it's just features. It's a vector. And I want to extract the steeple length. So I'm going to say add a new column to my data frame called steeple length. And I'm going to be getting the features column. And I want the 0th item from the features column. So let's take a look here. And now I have steeple length and steeple width broken out. Just an easy way to add additional columns. Notice doing this effectively requires you master data frames. The data science is easy. It's getting good at data frames that's the real work here in learning Spark machine learning. So we want to make sure we did it right. So this, by the way, was just a quick challenge. I'm going to go ahead and let you skip this challenge because I think it's less interesting. Are you guys okay with just running that solution? So you guys are welcome to run the solutions notebook or copy paste from the solutions notebook, and then at some point I will give you a challenge. And when you get to the challenge, I'm just going to say, clone the cell above and try doing this without peeking at the answer. So we're just going to work from the answers notebook so we can pick and choose our labs. You guys good with that? So you're going to open up Pipeline through Logistics Answers and hit Run All. Run the whole notebook, and we're going to pick and choose our lab. Now, how many of you guys wondered about using a user-defined type instead? Or excuse me, a user-defined function. Could I have done this with the user-defined function? Is anybody curious? Oh, I am. Okay. I wrote a user-defined function called getElement. There you go. Notice it takes a column object and a column object in this case. So the value, which is the feature vector, and I, which is a literal, and it returns a double. Because user-defined functions always require, take a look here, this is a column and a column. It just so happens this column will always have the value 0. And so 0 always got passed in as the value I, whereas the contents of the feature column for that row got passed into V. That's what literal meant. Does that make sense to you guys? Because what it's doing is it's going for each row, grab this column and this column for each row and put in the actual values here. So I needed something that for each row would always have the value 0. How'd you guys do with running? I was killing some time while you ran. Were you guys able to run the notebook? Anybody need another minute to run their notebook? To help you out, I'm going to show what lit does a little bit more vividly because I feel like my explanation lacked a little bit of substance. So let's come back up here. And this time around, I'm also going to go with column example and it's going to be a literal number 1. There we go. So just notice it's always got the number 1 over here. So now when it loops through each row, it's going to pass in this vector and that number into the UDF for each row. All I did is I effectively added a column that always had the number 1 for the purposes of the UDF. That's what's really happening. I couldn't just pass in the number 1 because what it's expecting is the name of a column, not the actual value. When I call a UDF, I'm giving it column names. So I had to wrap my value in a column. That's all that was about. Could I work with column indexes instead of names? Yes, I can. It's highly not recommended. But could I go iris separate features dot select? Actually, let me even think about that. What would it mean to select the first column? I haven't even tried this. That would be really messy. No, it's not going to let me select with an index like that. What I can do is go and convert it into an RDD, and at that point I can start grabbing things by index, because now they're rows. So I can start grabbing things that way, and then I could go 0 again, and I get the dense vector out. So I could do it as an RDD, but not in SQL, or not in the DataFrames API. All right, let's keep rolling here. So at this point, we've got our nice features, our sepal width and our sepal length features. Let's see here. Somebody had asked, could we instead use this built-in function called getItem? Unfortunately, getItem works on arrays, but not vectors. Worth mentioning. So we're going to skip past that. But if it was an array, I could have gone, give me the features column and give me the 0th item. That would have been really nice. But it only works on arrays. Question?
So what if we have 100 features? Should we use the list column this function 100 times? Is there a more scalable way to do it?
Well, so if you have 100 features, for example, odds are you're loading them from a data storage to begin with. What with column does is allow you to add additional columns, like derived columns. So maybe I had a column called birth date, and I wanted a column called age. I would add something called with column. I could show you later on another example that I have handy of with column where I wanted to find out how long was it since 1970. Like I just wanted some linear number representing time. So I called with column to subtract the time of that from the original epoch of time. So I added the column. I could show you some other examples later on. But all this does is let me add columns, derived columns, to a data frame. It's like doing a select star, comma, and then additional things. In fact, that's exactly how you would do with column if you were doing it in SQL. You'd select star, comma, and then additional columns. All right, so let's get to part 2. Now that we've actually gotten our data, we want to go ahead now and create a temp table called iris2. We're going to create a temp table called iris2. The other thing we're going to do is make getElement. We're going to register getElement in SQL. We're going to register our data frame in SQL. And what's nice about that is now I could do the exact same thing in SQL. For example, I could say, give me the sepal length. Sweet. It's a good example of using a user-defined function to process a user-defined type like vector. So now we can begin our exploratory data analysis phase. Has anybody got questions before I proceed on? I'm hoping you're really realizing that using data frames effectively, I keep harping on this, is the #1 key to doing data science on Spark. Calling the algorithm itself is easy. Processing data, that's the challenge. And processing it in parallel. So now, let's see here. What are all the different values that we might want to look at here? So let's take a look. I could say, describe to me the average sepal length, the average sepal width, and the label. So I have how many different unique labels? Well, there's 150 rows. They were 0, 1, and 2. What's the average of 0, 1, and 2? 1. What's the minimum? 0. What's the maximum? 2. These are our categories, right? What kind of flower was it? Very uninteresting. But what is interesting is notice when I go describe on a data frame, I'm able to get other kinds of stats on my columns, like what's the average sepal length, and I have no idea why the average is negative. Oh, it's probably been normalized, would be my guess. What were you going to say? It's most likely been normalized, because I don't think there's any flowers where the sepals like reverse and into the stem of the flower. So it's been normalized, which is a great thing to do, actually, on our data set. But of course, if it was normalized, I would expect the mean to have been closer to 0. But we may have done a random downsampling as well. And the min and max are what you'd expect between -1 and 1. Yes? Say again? Oh, could you actually select the ones that are nan? Absolutely. Go look at fn. There is an isNan function. You can search for nans. You could even go == nan. So you can absolutely ask which data frames have nans in it. Our data set has no nans in it, not a numbers. But you could absolutely take a look at the functions, and you can also just go == nan, because it's just typical IEEE floating point operations. So let's continue on here. So notice now it's actually not, this is normalized but not standardized in the sense that it goes between -1 and 1, but my mean is off, my standard deviation's off. This is not what I want for a good Gaussian distribution, is it? Now, I can do typical linear regression this way, but the moment I try to do ridge regression or anything of that nature, it becomes very important that it be standardized. So what I'm going to do is add a pre-processing step, the standard scaler. And I'm going to ask it to take the features, so it's going to read the features column and produce a standardized column. It's going to just add another column, and it's also going to try to make the mean center around 0. So I'm going to create this object. It's not actually done any work yet, and I haven't imported it. So let's import it. Let's run it. And now we're going to take the original data set, and transform it using our scaler up here. So first thing we got to do is call fit. Why? Because I'm learning. I've got to do some machine learning to figure out how much to scale it by based on the entire data set. So fit takes the entire data set and will learn a model to try to make it fit a standard Gaussian distribution. Once I've done that, then I can transform the original data set to fit that Gaussian distribution. So let's do that now and take a look at what it looks like. Notice here what it's done is it took the features column. I hate it's doing that. There we go. It took the features column, standardize the vector into a standardized column. Now, how did it know to do that? Let's scroll up again. Input column is features. Output column is standardized. So let me take this code. I'm going to get rid of some of the garbage in here for a moment. Get rid of this. Input column is features. So, and out comes the standardized version of features. So now I could actually have some fun. I could come back up here, and where was the code that we used to get the description? Describe. And so now I can call, well, in order to call describe, remember I've got to extract the length parameters out of here, right? I got to extract the length parameters. So how do we get the length parameter out of here? Out of the standardized features. You guys remember? With column and get element. So I've got the new standardized column. I want to grab the 0th entry and call it standardized length. And when I do that, what am I getting? A standardized length here. So what should the description of the standardized length be at this point? If I come down here and call describe on standardized length, what do I expect? If I've done a proper Gaussian distribution, the standard deviation is 1, and the mean is 0. Fits a standard Gaussian distribution. So this is a very typical processing step that I would do on any lab, and I consider it so important that you be able to do this that I want to make sure that everybody has a chance to run this. Now, I believe all this code was provided to you. There are no fill-in steps, correct? So go ahead and run these, but I really want to make sure everybody understands how to take a data set, and I really, really want to make sure everybody understands these parameters here. Take this column as a list of vectors and produce a new column after applying it to standard distribution. Now watch what happens if I was to set with mean off. What do you think is going to happen? If I set with mean off and then I rerun it, notice the standard deviation is 1, but it didn't correct the average. It didn't center it around the 0. So if I was to draw a picture, originally I had this distribution. And this was like 20 or negative 20. This was like negative 10 or whatnot, and or negative 1, let's say. And then I redrew it so that instead it was a nice line that's centered around 0 and had a standard deviation of 1. That's all I've done. Very common when you're cleaning your data for data science, right? How many of you guys do this all the time in your work? It's going to be very important if you do ridge regression later. All right, so that was the one place where I think you actually had to, oh, no, that's not even where you had to type something in. So you're good so far. We've got the standardized length. Now, the other type of standardizer we could do is normalizer. So what do I mean when I normalize a vector? And let's assume for the moment that it's an L1 norm or an L2 norm. Let's make it an L2 norm. The length of the vector is going to be 1, right? We just want to make the length of the vector be 1. We could do that instead. I'm not going to have you do the normalizer because we've already done the standard distribution. But keep in mind, I could take this and I could just make it so that it sums to the number 1, or the sum of squares equals the number 1, and so forth. P here would be the norm that we're using. Trying to think what's the best part to let you fill in here. Do you guys want to try doing a normalizer right now? Do a little hands-on? Let's go ahead and do that. Let me have you try creating a norm. So here's what I'm going to do. I'm going to have you open up. I am going to go ahead and have you open up the pipeline logic. I want you to open up the student version. So instead of the top, you're going to open the bottom. And I'm just going to give you 5 minutes right now because I want you, the real skill that I want you to practice here is not, oh, I understand this code. What I want you to practice is, could I figure out this code when I go back to my office? So how are you going to figure out the documentation for Normalizer? Let me just ask that question. If I give you the import statement, how would you figure out what to use? Anybody? You can go to the website, or I could use help, assuming you're in Python. And it tells you everything. I would recommend going to the docs on the website. I'd like everybody to do this to-do now. I'm going to give you a time-boxed amount of time on it because it's not critical path, but it's a critical skill that I want everybody to get. How do I figure out how to do these transformations once class is over? How many people need more time? Nobody needs more time. One person needs more time. You're done. Okay. Let's keep rolling then. So the point of this exercise there was really just to have you look up the docs and see how to use these transformers. They're extremely helpful. We need a joke here, right? So somebody gave me this joke over break, so if you don't like it, it's not my fault. 3 statisticians went hunting. The first one shot 2 feet to the left. The other one shot 2 feet too far to the right. The third one said, "We got it!" All right. So here we have part 3. So we finished going through and we finished normalizing our features. I really wanted you guys to get a chance to actually use these transformers. How many of you guys noticed that when it came to normalizing, it was just calling transform? But when it came to standardizing, way up here, I had to call fit and then transform. Why do you think that is? Why do you think that is? Exactly. If I'm standardizing, I got to actually collect stats about the entire data set, which returns to me a model. And remember, the model is then a transformer. Whereas normalizing, I could just go row by row. There's nothing global I need to learn. I just go row by row. So if we came down here to normalizer, notice we just made the normalizer, and then we used the normalizer. I didn't have to learn how to normalize things, whereas I had to learn how to standardize things. Very important insight. All right, you guys ready to go to step 3 here?
In principle, you wouldn't do it that way, right? Because you want to keep the model that normalizes for you, right?
Well, so normalization, I don't actually need to learn a model for normalization. I need to learn a model for standardization because I need to look at the global list of data to figure out how to make it fit a standard distribution. What was your question, though?
The reason why you have to do it first and then transform is because you're simply training it first and then you're transforming the data, right? So normally you wouldn't do it in one line, Eventually that comes in, right?
Correct. So you're absolutely right. So that was actually a valid point. So he raises a really good point worth mentioning here. He says this code really should be written slightly differently to be more generally useful. Because I have my training data, and in my training data, I want to learn how to normalize. So I might have my iris standardizer, which is this thing I did called fit on. And then I might take that and use it later on. So instead of doing all this in one line, it's very appropriate that I'm going to learn the standardization once and then reuse it even when new data points arrive. Even when new data points arrive. Because I might have an initial set of 1 million, and then I get another 10,000 rows. I could standardize across the 1 million plus 10,000, but that's time consuming. Or I could just apply the old scaling to the new data that's coming in. And then recompute my scalar once a day. And this is very common for streaming machine learning. Question? Okay, say it one more time. So that here, I'm learning a model for how to scale my data over my training data set. Now let's pretend like I had new data come in. So let's actually really make this realistic. Let's say I had iris training and iris new data equals iris separate features dot split 80% and 20%. And now I'm going to train it off my training data. And then I have new data come in. Well, I'd like to make sure that my new data gets scaled the same way as my original training data. So that's what I'm describing here. No. Oh, yeah, but that's a problem, but there's another problem too. It doesn't like the name of my original data set. What was it called? Iris separate features. There we go. Misspelled separate. And it's called select sampled. Random sample. Random split. Gosh. Random split. Thank you. Random split. So now let's pretend like I had training data and then I had new data arriving. I would learn how to scale it based on my original training data. But then as new data comes in, I'm going to also make sure that the new data fits that curve. Does that answer your question, whoever asked it? Perfect. Now, you would use this, of course, if you were doing training and test data for cross-validation purposes, but you'd also use it if you had streaming data points coming in. So that's right. Like overnight, when I've got a much larger data set, I may want to retrain my scalar. I want to retrain my model periodically, but as new data is streaming in, I don't have time to retrain my model. I just want to make predictions, spam or not spam, spam or not spam, as mail's coming in. And then every night I'm going to relearn what it means to be spam or not spam. Say again? You could do it based on a window function, but then you still want to decide how frequently you're retraining your model. So the window function itself is not going to be sufficient because you would be retraining at every batch interval. But that's getting off topic here, so I won't go too deep into the streaming. All right, now back into the questions here. So we did normalizers. You guys had a chance to do that. We did a feature norm. All right. I'm going to fail my tests, however, if I don't go back and fix something. I was training based on half of the data set. My test cases will fail. So I got to fix my model. There we go. So now we're in section 3. Where is section 3 beginning? I lost it. There you go, section 3, part 3. So now, you guys did normalization. We could do a sanity check and just make sure that all of our norms, in fact, equal 1. Except for our electrical engineer. Her norm equaled not 0.999999999. All right. Now, another thing that's very common in any kind of classification is what's called bucketization. How many of you guys are familiar with bucketizing things? Perfect. So in this case, what I'd like to do is to take my data and identify everything that is between negative infinity and half a standard deviation and put it into one category. Everything between half a standard deviation and 0 into another category. 0 to 5 and 5 to infinity. So we're just going to group these into buckets rather than being continuous numbers. Very common to do that when you're doing any type of classification problem. So again, we've got a feature transformer called Bucketizer. Now, does Bucketizer have any kind of global state I need to learn? No, I just give it ranges, and I'm done. So notice it's just a simple transformer. I say, given the sepal lengths, I want you to decide which bucket it's in. So I'll call transform on it and display it. Let's take a look at what happens. Notice now, length features, some of them are in bucket 0. Some of them are in bucket 1. Some of them are in bucket 2, and so forth. So I'm able to discretize this number into different buckets. Question? So you're asking, can I set the bucket sizes to get roughly the same number of observations in each bucket? So you've got a standard Gaussian distribution. So how would you do it? Well, there's a standard Gaussian bucket intervals that would give you, on average, the same area under your curve. And that's the way you would do it. Because if you wanted to do it based on precise counts, you'd have to now learn a global model. And that would be rather painful. So just use your standard Gaussian distribution. Everybody understand that question?
Do you have a component that would do it based on standard counts?
Do we have a component that would do it purely based on count? I do not believe we have that component. Let me check with my subject matter experts here. Do we have anything that breaks it into buckets based on absolute count?
The same way as you would train basically any other.
Just get for a discretizer.
Yeah, the bucketizer, but just wanted to make buckets the same size. Maybe you train others and then
Put it in the parking lot. That's a great parking lot question. I should have parked it right away. We're going to check into that. As far as I know, we do not have that feature. And you wouldn't want that feature because in a lot of ways that's a very expensive computation to do. Because you have to look at a whole global data set, and what you're really asking me to do now is to find the kth item, the 2 kth item, the 3 kth item. And that's a very expensive algorithm. Because you pretty much have to sort the whole data set. I mean, you can do it in less than a sort, but sorting is actually probably the fastest way to do that. All right, so that's bucketizing. Now, the last thing I want to point out here is that you can make a pipeline. So pipelines allow you to do a series of transformations all at once. So here's an example of a pipeline that's going to first bucketize based on length and then bucketize based on width. And for those who'd like, you're welcome. So we have the length bucketizer we've already run. We could do a width bucketizer as well. But I could make a pipeline that'll do both the length and the width at once. So we call that a pipeline bucketizer. And this is really nice here, because when I call that does not make any sense. Why would I need, oh, it's because it's a pipeline. So a pipeline bucketizer could do a number of things. We could actually, if we wanted to, let me make a more interesting case, not just do length and width bucketization, but also do our normalizations as well. So let me grab the, or better yet, let's say we're doing standardization. We were doing our standardization. Where was that? Iris standard scalar. I could come in here into my pipeline. Got to scroll down again. Sorry for all the scrolling. I know it's hard to follow. Here we go. I could do a standard scalar, then a length bucketizer, then a width bucketizer. So I could use a standard scalar to do that. And now remember, standard scalar required that I learn the model first. So I'll call fit. And notice that that returns me the model. And then I take the model and I can apply transform, and I get everything bucketized after being standardized. Question?
If those transformations are independent, will she do the training simultaneously on all? Because then when you guess the row, basically train multiple models in one app.
Okay, so
Will it do it? Because if they're independent, then it can't. They're independent transformations. Will it actually do simultaneously training of all of them?
So you're asking an interesting question, and it leads to a slightly greater theory, so we'll talk a little bit about it more later. But his question was, how does this get parallelized? There are two ways in which I could go about parallelizing any kind of machine learning. One way is to have one machine do this chunk of the data, and another machine do this chunk of the data, and another machine do this chunk of the data, and then have the machines talk to each other once per iteration, and iterate a few times until I stabilize. This is what we call data parallel. And this is what we're doing here because we don't necessarily know, number one, our data is big. We're assuming it's huge, and I got to parallelize the data anyway. And two, we didn't happen to know for certain that the length bucketizer and the width bucketizer were totally independent of each other, because they were both definitely dependent on the scaling that was happening first. There is another model of parallelization that we're going to see later on where we say, you know what, our data isn't that big. I could fit my data on one machine, but I actually want to train this model on that machine, and this model on this machine, and this model on this machine, and we call that model parallel. We'll look at that later on when we do some stuff with scikit-learn. But in this case, it's data parallel. So what it's doing is taking all the data and applying each of those, and then I don't need to worry about whether it's independent or not. Can you repeat the question real loud?
That's per stage, not per pipeline. So you're only parallelizing the data per stage. You still don't get the total, right?
So fair question. Is it parallelizing per stage or for the entire pipeline? And the internal implementations get a little bit tricky there because it depends on the nature of the operation. So Iris standard scalar, I have to train the model. I have to train the entire model as a stage. Actually, as a job. You're asking how does this thing get parallel, like it's like a pipeline. The fit step would actually be running multiple jobs. The transform step could actually iterate through the data once and apply all three transforms at once. So you're asking how it's implemented. Training models requires multiple job iterations. Running things through transform can be pipelined in one job. Am I correct on that? Coming back to my subject matter expert. Perfect. We got some of the engineers at Databricks who wrote the code. So I always like to verify because he actually helped write the code. All right, so one more really useful feature, the vector assembler. So we now have two new buckets that we've created, length features and width features. So if we were to go back up to our pipeline here, notice I've got length features and width features. They're no longer part of my features column, are they? I'd like to make a vector out of these two columns right here. I'd like to make a vector out of these two columns right here. How would I do that? Well, that is one of the most useful features of all, called the vector assembler. With the vector assembler, you say, take these two columns of my data frame and make a new column that's got them as a vector. So let's just run this code. Oh, I got to import it first. And that means I got to import this first. All right, now we'll run this. And now run this. And notice now that I have a new column called features bucketized that says 0 and 2. So the first one is 0, the second one's 2, so 0 and 2 got thrown into a vector, 0 and 2. Here, 1 and 3 got thrown into a vector with values 1 and 3. So just like before we were taking things out of a vector into columns, I can do the opposite. I could take columns and throw them back into a vector. That's known as the vector assembler transformation. This one is so important that I would like you guys to make a space above the answer, use the help, because we've imported all the code up above, use the help and figure out how to add the vector assembler to our pipeline. So I want you to come up with that answer, but I want you to try to really think through it by not looking at the answer key. I want you to use vector assembler. It's very, very important. I use it all the time in my work. Do you use it a lot, Waleed? Waleed uses it. Who else does a lot of machine learning with pipelines? Anybody in here? There you go. Oh, you wrote the code. That doesn't count. How are you guys doing figuring out the vector assembler? Who's still scratching their head on this one, sub? How many of you guys just copied the solution and said, I can figure this out later? A fair percentage of you guys. How many of you guys went and looked up and found the discretized quantizer to the earlier question about coming up with buckets of relatively the same size? It does exist. It's called the discretized quantizer transformation. And it works by doing a sampling and then doing the kth element of a sample. So it's approximations, but it's still pretty good. Quantile discretizer. And you just have to go and look at all the transformations. Say again? Unbalanced data sets. Can you elaborate? Ah, okay. You found that the quantizer is one of those things that's available in Scala, but not yet available in Python. So A lot of the newer ones typically take a little bit longer. Now, the thing you can do is you can look at the source code for how all the other ones in Python were linked in and throw in that little bit of source into your notebook, and now you'll have it too. So I've done that on a handful of times. You actually look how it's, because the Python is actually calling into the Java, and you can look at exactly what code it put in there. So I've had to do that on a handful of times. Give me one moment. I'm going to show you a nice example of putting all this together. It's one I wrote for myself, and I will upload it to the website as well. So for the moment, I just need my password. Are we due for a break yet? In 13 minutes. Perfect. So this would be a great way to end before a break. And then we'll get into doing something really cool right after break, where we're going to call scikit-learn. So I'm going to bring all this together with one comprehensive example. I just want people to follow me for now. I'll zoom way in. I will give you a copy of this code a little bit later. I'll have to export it, and you guys will be able to import it later. The reason I'm not going to have you run it right now is that it's relying on a local table that I've set up, and we don't have it set up in your shard. But I wanted to show you a very realistic, real-world analytical example from beginning to end. So right now, I've got a table called page views by second. And let me just show you what that table looks like. This is Wikipedia data now. It's a lot of data, so it runs a little bit slow on CE. We're going to cache it. But notice it's at this second of the day, Wikipedia's mobile website got this many requests. And it's a simple comma-separated values file currently. It's not even a Parquet file. Now, the timestamp, if you look at it, the timestamp is currently wrong code. Interpreted as a string. And I wanted to convert this into an actual timestamp object. So you see how it says string there? Do you need me to make the font any larger? A little bit? There we go. Notice the timestamp is a string. So what I'm going to do is I'm going to add a new column, and in this new column, I'm going to cast the timestamp into a timestamp type. And I'm just going to make the new column also be called timestamp. So I run this code. And now I've converted it into an actual timestamp object. Now what I'd like to do is, I'm going to jump ahead and give you an idea of the problem I want to solve. This is the traffic that's happening at Wikipedia, varying by the time of day. And you can see the desktop site and the mobile site. Now, what I'd like to do is to reduce the hourly totals, or excuse me, reduce our data from being per second to being per hour. So I'm going to have to do a series of data frame transformations I'll show you later on and graph it. And now you get a much better picture. And I'm going to walk you through some of the code, but I've reduced it to how much traffic the website is getting per hour of day. And what do you notice? Some hours of the day have more traffic than other hours of the day. Like at 10 p.m. at night, very little traffic. Oh, this is Greenwich Mean Time. So 11 Greenwich Mean Time would be like 3 a.m. U.S. time. Is that about right? Somewhere around there. So it'd be very low traffic. Compared to, if we come up here, 2100 Greenwich Mean Time would be right in the afternoon U.S. time. So notice that it's cycling per hour of day. It's also cycling a little bit. There's this meta cycle for day of week, where weekends might get less traffic than weekdays, or maybe more traffic. But there's a meta cycle for the day of the week. And then there's occasionally these incredibly anomalous events. This is April 20th. I can't imagine what people would have been Googling on April 20th. We could go and find out, or you could probably take a wild guess. But there's an anomaly with a lot of traffic. So my goal is to build a machine learning model to predict how much traffic there is. Very typical data science example. So let's take a look at how we combine everything we just learned, everything you just learned, to do exactly this. So the number one thing I've got to do is take the data you saw before, and I need to add new columns like hour, day, and date. So let's take a look at what that would look like. So now I could have the day of week, the hour of the day, and how many requests occurred during that hour of the day. Now that's just a lot of data frames code. So this was pretty fancy data frames code, but notice that I'm taking my original data and I'm grouping by the day of week and the hour of the day. Or excuse me, the day. I'm taking the day. What am I doing here? Day column is, yes, the day of week. And I'm also grouping by the hour of the day. Oh, and I'm going to sum up all the requests. So I've summed up all the requests. And then I'm going to order it by date time. And that's what gave me this nice chart. This day at this hour, so this day of week, at this hour, had this many requests. I probably didn't even need the day column, actually, in my group by, but I wanted to have it in my data set. But for each hour, I have the total number of requests. I could maybe want to split out calendar day from time, and in fact, I do want to split out calendar day from time. So what I need to do next is to do exactly what you said. Split out calendar day from time a little bit. So I'm interested in knowing what hour of the day it is, what day of the week it is, and how much time it is since 1970. I'm trying to extract my features. And so this was just a matter of doing more data frames processing. All I'm doing here is I'm saying take the date time column, turn it into a double, and call it hour. Take the date time column, take the day of week as a number and subtract 1 so that Sunday is 0, and call that the day code. Or take the date time, turn it into a timestamp, and then cast the timestamp into a double, and call that the Unix time since 1970. And I just select those additional columns. So here's my select statement using each of those expressions defined above. I'll give you a copy of this code. Notice how much work is really data frames. Now that I've done this work, what I want to do is create a feature. And what should my feature be? Hour, day, and time in Unix format. And I want to predict the total number of requests. So which object would I use to create a feature vector out of columns? Vector assembler. I expected everybody to answer that. Let's try this again. Which transformer would I use to create a vector out of several columns? Much better. Vector assembler. You guys are awake. So here's what I want to do. I'm going to make a vector assembler. But before I do a vector assembler, there's something very important I need to do with this data. Something very important I need to do with this data. And that is, do I want to, if I'm doing linear regression, do I want to assign the same weight for hour 0 that I do for being hour 1 versus 2 o'clock in the morning versus 3 o'clock? That would imply that traffic is going up and up and up and up. I hit midnight, and then it goes up and up and up and up and up, and I hit midnight if I was to give the same weight to every hour, wouldn't it? But it's supposed to be cyclical. So what feature, data scientists, we haven't learned this one in class today, but you're data scientist, how could I take a feature where I want each value to actually get its own weight? What do we call that? One-hot encoding. How many of you guys know one-hot encoding? Right, so one-hot encoding, really simple. Instead of representing it as the number 5, I'm going to represent it as, instead of one variable, I'm going to represent it as a bunch of variables, one of which will be true, and all the others false. And now, when I do my dot product, I can multiply this guy by 0.1. Let me decrease my font size a bit. I can multiply this guy by 0.2. Multiply this guy by 0.3, depending on the time of day. Then I could start de-emphasizing again. By taking one column and making it many columns, I can assign different weights when I learn this model. Very common in your data science, called one-hot encoding. So I'm going to use that. Let me, let's see here. If I wasn't nervous that the code wasn't going to run, I'll run the code again a bit later. But I want to make sure this works first. So here we are. I have my one-hot encoding. I'm going to take the hour, and I'm going to turn the hour into a vector. 0, 0, 0, 1, 0, 0, 0, 0. I'm going to take the day, Monday, Tuesday, Wednesday, Thursday, Friday, and encode that into a vector where it's only 1 for the specific day, and all the other days it's marked 0. So I can assign a different weight to every day. Then I'm going to take the time, the day vector, and the hour vector, and what column am I going to make? Features. That's the job of the vector assembler. But I want to do ridge regression. So what do I need to do? Standardize it. Now I have standardized features. So now I'm going to do linear regression. I'm going to read from the standardized features and predict, or excuse me, I'm going to read the standardized features and train, do my training column, will be called total requests. When I'm done training and I do predictions, I'm going to put the answers under predicted total. And I'm going to do ridge regression. So here's the value of my regularizer. If you don't know what ridge regression is, don't worry about it. It just tries to avoid overfitting of my data. So now look, I've got a pipeline. Encode the day, encode the hour, vectorize it, standardize it, and do linear regression. And now I got a pipeline. Question in the back corner. Could I take care of throwing out outliers? So that's a fair question. I'm going to show you an example of throwing out outliers a little bit later, because there are various methods for throwing out outliers. One is I could, throw out everything with more than one standard deviation away. That might be a very good way to do it. What I want to do is train a model and throw out outliers. So I'll show you that in a minute. But there's several ways I could throw out outliers, and that might be worthwhile doing, as long as I'm willing to accept that I'm not trying to predict those anomalous days like April 20th. Question here.
The better explanation be, instead of treating the R on the days as a continuous variable, we're actually using it as a discrete variable rather than the way we do this.
That's right. Rather than saying I'm going to multiply the hour of the day by some fixed number, I'm going to instead say you're either 1 o'clock or you're not. You're either 2 o'clock or you're not. You're either 3 o'clock or you're not. And that's why one of them has the value 1 and all the others have 0. And that allows me to give a different weight to 1 o'clock compared to 2 o'clock. That's a good way of describing it. Thank you very much for one-hot encoding. Question here.
Yes, regression, typically the regressors or predictors are supposed to be independent of each other. But in this model, when you have a time series, you expect them to be all regressive a little bit, right? Do you see that in your residuals later? Maybe I guess we'll meaning if the traffic is high at 5 o'clock, you expect it to be high at 6 o'clock, not suddenly jump to like this, all regressive. It's not like true IID, right?
So we are not doing a true time series prediction.
But it is a time series.
This is time series data. We're not doing a time series prediction for one very simple reason. The time series features are still being added to Spark. So you see some open source libraries that people are adding to do time series analysis, but it hasn't been rolled into the core product yet. So I'm simulating in many ways time series by just bucketizing things. And that's a very easy way to do it, is to just put times into buckets and then assign the weights. But it would be nice if I could do a time series. I could even do a Fourier analysis on the time series. But I'm limited to, in this case, some of the features available in Spark, and we don't have good time series libraries yet for Spark. Let's go ahead and finish this off. Let's add more questions to the parking lot, unless it's a comprehension question for what we just covered. I really appreciated the gentleman who gave a good short explanation for one-hot encoding. But feel free to add things to the question parking lot. That's what it's there for. We will answer those questions.
Where is this notebook?
I'm going to upload this notebook to the website. So you don't have this notebook. I just decided last minute to grab it. It's an example I whipped up on my own. And I said, this is a great example of vector assembler and bringing it all together to solve a real-world problem. So I will upload this notebook. I would actually, the trouble is you guys would have to each import it one by one, and I don't want to create that chaos in class. So I'll put it under the file share. I'll put it under the data science file share, and I will upload the data set that I used as well. So then I got a pipeline. However, the pipeline describes the process I want to use for learning. I still need to train my model, right? So we come down here, and I say, here's my data set, train a model. Now, I want to see how well my model fits. Now, I'm going to be sloppy for the moment, and I'm going to test it with my training data, just to see how well my model fits the global picture. So I test it with my training data, and take a look at this picture, by the way. So remember, we had hour, day, and Unix time. Notice that the hour became a vector. The day became a day vector. And then all of those vectors combined became my features. Once I standardized my features, I got my standardized features. And eventually, I got my predicted total. Notice it's just adding columns to the data frame as I go. And what I'm curious about is, how did my predictions do versus the actuals? So let's take a quick look here. Let's do a plot. Did pretty good. Now, when I first did this lab, I started out with linear regression and got this beautiful plot. And then I said, you know what? Let me use a decision tree instead. Decision tree is just a different way of doing prediction. Now, ironically, my decision tree predicted this anomaly perfectly. Why? Because it said, if date is April 20th, multiply everything by this factor. That is a classic example of overfitting. So what I should have done is trained it on 1 month's worth of data and tested it on another month's worth of data. Now the irony is when I first did the decision tree and I wanted to test it, I did random sampling. And it was still overfitting. Why? Because I was getting random samples from April 20th. So I still had overfitting. I needed to actually do random time intervals instead to avoid the problem of overfitting. But if I wanted to switch this to being decision trees instead of linear regression, it's actually an absolute piece of cake. Instead of calling linear regression, I just use the decision tree. And I'd have to get the appropriate parameters here. There's not like a regularizer. But I would just use a decision tree instead and rerun it instead of linear regression. And boom, I'm using a different algorithm. And when I'm finally done, the last part is evaluating how good my model is, which is something we haven't done yet. So let's talk about this. And are we already past due for break? Okay, break right now. You have 7 minutes to go get coffee. That's Jamie waving at me going, Doug, they're going to miss their coffee. Sure, come up and ask it during break here. So I'm going to see you guys in 10 minutes, because it's what, 4 o'clock? I'll see you in 10 minutes. It's a 10-minute break. All right, let's regroup here. So we have our agenda, and our agenda will be as follows. First, we have a review form we want to make sure we distribute. Please do it before you leave today. So I'm going to give you 5 minutes now to just get it banged out. If you say, no, I really want to see this last part before I give you a score, that's fine. But remember, the conference likes us to have 95% feedback, and I think I've lost a few people in the room, so all of you guys are on the hook. So this is very, very important. I'm going to be distributing that link momentarily. The next item of business, short joke, and then we're going to wrap up doing some validation. So I'm going to do test and training sets. And then we're going to do a grid search. And I'm going to jump straight to an example of doing grid search instead of what we've been doing, which is data parallelizing the training of a single model. We're going to do an example of grid search where I'm going to do model parallel. That is, I'm going to try different hyperparameters for my model and train multiple models in parallel. And then the last item is, with any time remaining, we're going to have a Q&A session with our subject matter expert who's been assisting us with developing our class here, Waleed, my co-instructor. Now, are there any other requests before we bring that home? Is there anything else that was really important that we're missing? How are you guys doing? Are you really seeing how the data frames ties in with these transformators and estimators to solve real problems? And of course, the open question is, how do I do cross-validation and other types of work, correct? Am I missing anything essential that you came for? Yes?
Earlier you said you were going to talk about taking care of outliers.
I will show an example of the way I chose to take care of outliers. There are a few transformers that can also do quantile analysis to take care of outliers. Or what you could do is standardize your curve and then just throw out any data that's outside of a particular standard distribution. But I'm going to show an example of where I actually threw out outliers a slightly different way. So I'll pull that up. So I'll throw that in here. It's actually part of this example. So we'll definitely do that. Before we go any further, though, I want to make sure you guys know where to find the link to the feedback forum. Your feedback matters. In your feedback, please tell us what you really liked, and please tell us how we can improve this class for future audiences. So data science is by far one of the most challenging classes we have, because the hard part is the vocabulary of the data science, and yet most of you guys know the vocabulary of the data science, and the real work is massaging and manipulating the data, getting it into these estimators, and just applying these libraries to solve real problems. And yet at the same time, I'm sitting here introducing standardizers and normalizers and quantiles and bucketizers and vector assemblers, and what are all these pieces doing as part of my pipeline? And what I want you to do is to get these critical concepts, the way to use data frames to get your data into shape. Most important, 80% of your work is data frames. Then setting up your pipeline. And nobody builds a pipeline without referencing the documentation, which is exactly why I had a lab where I said you're going to have to go look at the documentation and make this happen. You build your pipeline, and then you start analyzing your results, and analyzing the results is what we have left here. So if you haven't, that's the pre-class survey. Where is the post-class survey? Does anybody see that in here? Class feedback form, right at the top. Class feedback form right here at the top. You just click on it, you open it. I'm going to give you a few minutes right now to submit feedback. I love really valuable suggestions as well as what really worked. So that way we don't throw the baby out with the bathwater, right? We want to know what worked, what to improve. Your feedback matters. Say again?
I can't get to your URL.
You can't get to the URL?
No, it's not your fault. It's because I'm on the PLC network.
Oh, it's blocking the form?
Yeah, so when I get back to the hotel, okay.
Appreciate it. As long as you promise me you'll do it at the hotel, we're good to go. Your feedback matters. So you'd actually have to go back and look at the news story. There were two big news stories. For this one's kind of curious. There were two big news stories on April 20th. One is, yes, the 420 article got a lot of traffic for grins. There was also, if you go back to Google News for April 20th, 2015, you would find some, I think there was one or two big news events on April 20th. So two things caused that spike in traffic. I'm pretty sure it was people had fun hitting that article. I remember going through and looking at exactly which articles had a spike in traffic, which is a much bigger machine learning task to do. Anyway, I'll come through and I'll answer a lot more of these tasks later on tonight. I just wanted to give everybody a chance to submit their feedback forms. Most of you guys have. Thank you very, very much for your feedback. I really appreciate it. We are getting ready to try to create a company-wide at Databricks machine learning curriculum. We've been developing it at Spark Summit Wests, and we want to keep developing it to really be what people need on their jobs, at their companies. So all of your feedback saying, here's the kind of course that would really be powerful for the company is really powerful for me because I'm responsible for the training program at Databricks. And you're welcome to email me afterwards. I'll give you my email address as well. All right, so let's go ahead and get this thing wrapped up here because we only have half an hour. So thanks again for your feedback. So we talked about vector assemblers. Oops. And I promised you I'd show you a few other little examples here, and I will make this available to you guys after class. So there's a few things left that we need to cover. Do you guys need a short, very short joke just to get your head clear? All right, let's see here. Can I come up with a joke off the, which jokes do I got left? Okay. Guy's walking outside, and suddenly he hears somebody calling down from a balloon above. And the guy says, "Hey, down there, can you tell me where I am?" The guy says, "You're in a balloon, approximately 25 feet above the ground." Guy calls down, "You must be in IT." "Yeah, how'd you know?" "Well, your answer is technically correct, but does me absolutely no good." The guy calls back up, "Well, you must be in management." "Yeah, how'd you know?" "Well, you don't know where you are, you don't know where you're going, and somehow it's my fault." All right, I have to give credit to one of the other trainers who shared that one with me. All right, so here we go. Step 7, evaluation. So here I'm not going to do a full grid search, but I'm going to do some basic cross-validation. So what I'm going to do is I'm going to split up my data into a training set and a test set. So it's just an 80-20 split. Now notice that when I do a random split, what's actually happening is, in order to do this efficiently, it's not going to go and count the entire data set and decide, okay, this many goes into 80% and this many goes into 20%, because that doesn't scale. Instead, what it's going to do is roll the dice for every row. So there's an 80% chance this row ends up in one data set, a 20% chance that this row ends up in the other data set. Now, given this random element, let's just do this without a random seed for a moment. Oh, right. I may not have the table mounted. Let's find out if it runs. It is running. This is a good sign. And if I ran this multiple times, the number of rows in each set would vary. Now, how much do you guys know about the way Spark gets fault tolerance? Well, the way Spark gets fault tolerance is very simple. If a machine dies, it reruns the code to reproduce the data that was on that machine, and it runs it on some other machine, because it remembered all the work you did before until you called cache or saved it to disk or whatnot. Actually, cache would be in memory, it'd be gone, but there's other cache options that make backups. So if I do a random split and I don't specify a random seed, and then I have to rerun my randomization, what's going to happen? I'm going to get some data in both data sets by accident because one machine just redid its randomization. So in order to avoid this problem, it helps to just make a random seed. The meaning of life, the universe, and everything will be my choice of random seeds today. Or we could do in honor of the really popular Wikipedia article. It'll be up to you guys. Now, this is California after all. Now, once I've done that, I can create my testing model based purely on my training data. So notice I got back an RDD, or excuse me, a data frame of test data, or training data, and a data frame of test data. And from there, I can actually train my model on the training data and then apply it to my test data and see how I did. And I could even get a nice little plot. And you see, okay, it's not quite as good as it was before. And in this case, I did it randomly, so I didn't separate different time intervals the way I probably should have. I just randomly selected points. But you can see I did pretty good on my chart with my predictions. We want to see how good did I do. Well, to figure out how good I did, this is the last part of the machine learning API that I want to show you, which is the evaluation, the evaluators. The evaluators allow you to look at test data's predictions versus total requests and figure out how we did. Now, in this particular example, this example was written before some of this was brought into the world of data frames. So I had to call into RDD MLlib rather than Spark ML's data frames module. So notice I went test results, give me an RDD, And for each row, give me the prediction in one column and the total request in another, and let's gather some metrics. Now this was written back in the days of, I think, Spark 1.5. Richard, tell me, has this been added to 1.6 into the DataFrames API?
Yes. It's regression evaluation metrics in the class of this.
Regression evaluation metrics introduced in Spark 1.6 or 1.6.1? 1.6. Introduced in Spark 1.6. So this code is a little bit stale. I had to call into the older MLlib because this was written in Spark 1.5. I did this last year before the Spark EU in Amsterdam. So, but notice now I can grab my root mean squared error, my explained variance, etc., and see how I've done. And we could even do some queries to look at how we did. And this is actually a good bell curve. You just can't tell for one silly reason. Notice that it didn't center this pillar around 0. When it plotted, it did this, everything up to 0 on one side and everything on the other side of 0 on the other, so it didn't draw perfectly. What I should have done was staggered this slightly. Oh, I did stagger it. I did stagger it over. I shifted it so that it would plot properly. So what you see is something resembling a bell curve, and all that says is that your errors are in fact normally distributed, or Gaussian, or standard distribution. Just saying, yes, I got a good normal distribution or standard distribution of my errors. And then we could go back and redo this with the decision tree. Now, I'm going to pull up the Scala version where I went a little bit hog wild. Because I first wrote this in Scala, so I'll distribute you the Scala version of this as well. And if we go in and we look at the Scala version, one of the things I could do is filter out the outliers, which was one of your requests. So in this case, the way I chose to filter out the outliers is I trained the entire model. And then I asked myself, select only the rows where the difference between the prediction and the total was less than 2 standard deviations. This is one way I could throw out the outliers. Train the entire model, figure out where the model did lousy, and throw out the data. Now, there are better ways of throwing out outliers. Absolutely are other ways of throwing out outliers. So take a look at some of the transformers that are available in the docs. You can do quantile transformers, etc. Here, I simply just chose ones where my model was wildly out predicting and threw out those data points and retrained. This is one of several ways. Richard, how would you do it? Or Waleed? Would you have done it this way, or would you have used a transformer earlier on to throw out outlier data?
This will work. There's many ways to do it, this will work.
I think the problem maybe with this approach is your model is already skewed.
My model is already skewed, but that's why I'm throwing out at 2 standard deviations.
But you're throwing out the results, right?
I'm throwing out the input data from 2 standard deviations, and then once I've thrown out the input data, I'm recalling fit and seeing how I did, and I regathered my root mean squared error and evaluated. So I basically just threw out data points when my model was wildly inaccurate. That's good to do if my model is overall sound and I had a few outlier data points. However, if my model was wildly inaccurate, then throwing out data points doesn't do me much good. It just helps overfit my model. So you have to be very careful in that regard. All right, we're running low on time, so I wanted to make, by the way, there's other things you could do. For example, you could actually do cross-validation in here. I'm going to show you an example of that a little bit later. You could do a number of other things like using a tree validator. I'll leave all those for you for exercises. You have all of these labs You have a whole variety of labs that you can play with. So there's a variety of labs doing, for example, TF-IDF on Wiki. We deliberately gave you way more material than we could possibly cover in a class, trying to make sure instead that you have plenty of things you can play with after class, and you can take all of this with you. What I want to do right now, though, is two very important last steps. Can you pull up and figure out which example had the cross-validator in there? Meanwhile, I'm going to pull up the other lab. I just need to figure out which lab it was. Meanwhile, we're going to come over here to scikit-learn. And I'm going to show you the other really cool example. And I'm going to do this as a demo, time permitting. How many of you guys would like to go and apply an algorithm that's not available in Spark? You don't have super huge data, but you want to be able to try different hyperparameters and do your cross-tabulation, or cross-validation of different hyperparameters in parallel. This is what this example is a demo of. So go ahead and pull it up, and go ahead and hit run all on use scikit-run locally. Again, we're dealing with our iris data set. While it's running, I want to highlight a few pieces of the code that's interesting. How many people here use scikit-learn? All right, about two-thirds or half the room. So scikit-learn is a very popular Python library for machine learning. It doesn't do data parallel the way we could with Spark. It runs only in the local machine, but it's able to gather a lot more data because it can compute covariance matrices and other things. So I'm going to use scikit-learn's k-neighbors classifier from scikit-learn. What I'd like to do now is to do a grid search. So I'd like to run the nearest neighbors algorithm with various values of k. So I'm going to run the scikit-learn nearest neighbors algorithm with various values of k. So take a look here. K in this case is a hyperparameter. And I'm just going to choose the k nearest neighbors. So the number of neighbors is k. And I want to run this many times in parallel. The way I'm going to do that is to use RDDs. So remember I told you RDDs are good for really two things. Number one, they're good for reading unstructured initial raw data, text, and turning it into something structured in memory. So, JSON text is unstructured until I parse it. And then it becomes structured tree data. So RDDs are really good about reading an input file and turning it into something structured. The other thing they're very good at is when you want manual control of parallelization. So in this case, I'm going to make an RDD with the numbers 1 to 10. And I'm going to make it be in 10 partitions. So I'm making an RDD of the numbers 1 to 10, and I'm going to split it up into 10 different partitions. So that 10 tasks will run in my job, potentially on 10 different machines, assuming I've got 10 machines in the background. Now, what's the job I want to run? I want to run the nearest neighbors once with the value 1. So here, let me just write this in a little bit clearer for those of you who don't like range. I've got an array, of 10 numbers, and map runs this function once for every item in this array. Now, what is this function doing? Well, let's scroll back up. This function is calling nearest neighbors and trying a different value of k. Now, who is it who wanted to try linear regression and decision tree? Who was that? Nothing's stopping you from actually specifying the entire model as the parameter right here and passing in, not the model, the estimator. You could actually create, item 1 could be new decision tree estimator. And then this could be new linear regression estimator with a hyperparameter of 6. And then new linear regression estimator with a regularizer of 0.5. So you could actually pass in the entire object here that you wanted to run on. It does have to be serializable. Fortunately, estimators are serializable. So you're in good shape. And now notice that it's running the k nearest neighbors multiple times and showing me the result. So this is what's known as model parallel. Rather than trying to do massive big data, I'm doing medium data that fits in one machine, but I'm running it on 10 machines 10 different ways. And it's a piece of cake to do. Does anybody need me to diagram what happened in that task? How many of you guys are unfamiliar with RDD and map? Nobody. So you guys are good with what just happened in that code? Really, really powerful way to do a grid search. That one does have it. Okay. So the last one I'm going to show you is the actual cross-validation. Now, the cross-validation example I'm going to pull up from the Essentials class. So I'm going to come to Essentials. And I'm going to go to the machine learning module. They get to spend 1 hour. No, they spend about half an hour on machine learning in Essentials. And I'm going to pull up an example called ML pipelines. Here, you hear them in the other room? ML pipelines. They're right where we are, but they spent the whole day on RDDs and transformations and actions before they got here. So let me run this guy. Where's run all? Oh, I have to control 0. Run all. So, anybody here an electrical engineer, or excuse me, anybody familiar with how power plants work? Anybody remember their second law of thermodynamics? All right. So, if it's hot outside, is a power plant going to be more efficient or less efficient? Less efficient, because it's unable to get rid of all the heat as efficiently. And so the old cycle is less efficient. So what we have in California, how many of you guys were here for the rolling blackouts a decade ago? Nobody? There you go, one person. So a peaking power plant, very simply, is a power plant that runs on natural gas during the hottest part of the day to add additional power to the grid. And we want to be able to figure out how many of these guys to turn on based on how much power and how efficient the plants will be. So what we've got here is a data set. Let's just look at the data set here. It's a data set. Atmospheric temperature, vacuum pressure, atmospheric pressure, relative humidity, and power output, or power efficiency. And I want to predict what kind of power output I'm going to get from my plant based on these atmospheric conditions. Simple linear regression idea, we would think. So the first thing we would do is our nice exploratory data analysis. So I might want to visualize my data. Now I'm here in the Databricks product, so I could quickly click on this chart and say I would like this to be a scatter plot. make this a little bigger. And notice I have a nice linear relationship. As temperature goes up, efficiency goes down. Except temperature should have been on the x-axis and efficiency should have been on the y-axis. So let's click Plot Options and reverse the two. There we go. As temperature goes up, efficiency goes down. And I could do the same type of exploratory data analysis, this time exhaust vacuum versus power. Again, I'm going to do a scatter plot. Size it up a bit. And again, I've got my x and y axis reversed. All right, so I get something pretty close, but there's something nonlinear in here. This is the art and science, or this is the art of data scientists trying to figure out whether a linear model would work with something like this. Maybe inverse vacuum pressure, or the difference in vacuum pressure from 40 would be important. Then we go down and we could plot all of these. In fact, I could plot all of these all at once if I really wanted to. So we have exhaust vacuum, power. Let's go back up to the original plot. And it goes scatter plot. Oh, that's the describe. Where's my original table? Here. Scatter plot. And I could plot all of them versus all of them if I really wanted to. And do a whole bunch of plots. And I'm able to notice definite linear relationships with power here. Which column is power? This one, this one, this one. Take a look at relative humidity. Humidity has almost no impact on the efficiency of my power plant. So this is power efficiency in this column versus relative humidity, atmospheric pressure, vacuum pressure, and temperature. Very quick data visualization as part of my exploratory data analysis. Once I've done that, and I've done all those visualizations, I want to build a machine learning pipeline. So what do I need? Vector assembler, exactly. I'm going to grab these guys and make a column called features. Then I'm going to split up my data. I'm going to train on 20%, it looks like. No, I'm going to train on 80%. My training set is 80%. My test set is 20%. And I'm going to cache my data set at this point and do linear regression. And then we look and see how we did. So I'll scroll down and look at my predictions. They're not bad. But wouldn't it make sense to try doing it with a variety of different values for cross-validation? So let me scroll down a little bit further. We could try decision trees. Where's my cross-validation? Here we go. Cross-validation. I make a new object called cross-validator. I give it my linear regression pipeline we had before. And I give it how to evaluate how good it is. So these are my regression metrics. And then I decide what are all the different values of the regularizer I want to plug in. So I give it a whole bunch of different values. In this case, 10, 20, 30, 40, 50, or excuse me, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, all the way up to 10. And then I simply say, I would like to make a grid with these different parameters. And now, watch this. I call crossvalidator.fit. And it's going to run this once, twice, 3 times, 4 times, etc. Look at how many total Spark jobs got kicked off. 185 Spark jobs got kicked off. So let me ask you the question, did it do it model parallel or data parallel? So what is it doing? Well, let's take a look at the jobs. Let's take a look at the jobs here. So the first time it ran, it's going and doing the job for one set of cross-validation, but it had to iterate, so it took about 4 times for it to converge. Then it went to run another job. Took about 5 times for it to converge. Then it tried another one where it was doing a different value of the hyperparameter. So it's trying each hyperparameter serially. Why? Because I'm assuming a big data set. So I'm going to train the data in parallel and do each model serially. That was the opposite of what you saw me do with scikit-learn, where it was small data, parallelized the training of the models. Here I had big data, and I did the models sequentially. Once I've done this, and by the way, this example is here for you to take home as well. Once I've done this, though, scroll back up again, I can then come down and ask for the best one. Where is the best one? I did it with decision trees up above. You can take a look at this. And random forests. And eventually I want to choose the very best one. So random forest model, give me the best model. And tell me what the values were. So give me the best model out of my cross-validation. And then here, stages, I'm trying to grab the last stage, which was the decision tree. And I wanted to look at all the inputs it used. And this part here, this is calling into the Java code because it's not available in the Python API. So it was literally jumping down to the Java object to call it. I think it's been made available in the Python API since. But I just grabbed the best model. So that's a nice example of doing cross-validation. And if you look at the Scala version of this, it then takes that model and pipes it through streaming. So, real temperatures are coming in. How many power plants should we turn on? Which is a really cool case study. So feel free to take a look at this one after class. So we are out of time. I'm going to go ahead and let people go. Those who want to stick around and have a Q&A session with Waleed and Richard, you guys are welcome to. I really hope you guys got a sense of how to build these pipelines. And any suggestions you have on how to keep the class covering the variety of topics and at the same time being more hands-on, I really want to hear your ideas. Because in my view, I want to get you more hands-on, and I really need your tips on how to make it the right balance. Did you guys learn a lot today? Excellent. Thank you guys very much for coming.